So my name is Scott Breitenfeld. I'm from the HDF group, and I'm going to talk about the HDF5 library. So I'll first start off with the foundations of HDF5, what is HDF5, and some HDF5 fundamentals. I'll try that with a simple problem. And then I'll go on to introducing some HDF5 performance fundamentals. First would be discussing raw data rights with some metadata impacts, and then tuning the metadata itself for parallel HDF5 applications. So what is HDF5? It's a hierarchical data format version 5. It's extensible data model, meaning that you can put structures for data organization and specifications within the file itself. It's open source software that includes both the IO library itself and the tools that it comes with. And you can, it performs IO on the data organized according to your certain data model that you came up with. It works on POSIX and other type of backing stores such as object stores, Deos, AWS, Azure, and different types of memory hierarchies and other storage devices. It's also an open file format. This is for POSIX storage. If you start talking about the object stores, that's not necessarily the case. So this talk will focus mostly on the traditional POSIX file systems. Now, when Aurora comes online, you have Deos, then this talk will start to address the quirks of Deos in that file system. But for this talk, it's mainly focused on the current widely used POSIX systems, parallel file systems. So HDF5 is designed for high volume and very complex data. It's not uncommon that you have HDF5 files that are gigabytes or terabytes in size. It handles basically every size and type of system. It's very portable, so you can take it from your laptop or your exascale and run it and open that same file on a simpler system or a different system. It doesn't even have to be on the same architecture. It's very flexible, so you can store. You can rewrite your data model as you see fit, and the backing storage is very transparent to the user itself, so you don't have to change your API, even though you've changed how you're storing that data. It also enables your applications to evolve the HDF5 file that you've created, so you can add data to that file, remove it, rearrange it, however you see fit. And if long-term data preservation is important, and this HDF5 is very good for that. We have NASA has a lot of archives in HDF5, and it's very important for them to have that data around for a long time. Let's discuss now the HDF5 data model itself. So HDF5 is just a structured container that holds the data objects. And what I mean by data objects is, first off, you have your data set and attributes. Those are how you contain your data. So the data sets are the actual data elements. And say you want to add units to be associated with that data set, you would usually use an attribute. So those are user-defined type of metadata that describes what the data set is. Related to data sets and attributes, then you have data space and data type. So data space essentially describes the layout of the data sets or the attribute. That's the data elements. You also have associated with the data sets your data type. So it describes whether it's an integer or float or whatever or a character or a string, whatever you have there. And then finally, you obviously want to organize your data sets and attributes in a certain manner. So you can use groups to put those data sets or attributes in to organize the data. You can also use links that essentially can point to a data set or attribute from inside the file, or you can point to another data set in an external file, HDF5 file. So with this shorter talk, it's not really feasible for me to get into the specifics of how you would do HDF5, but there's lots of resources to help you get started with HDF5. So the first is our homepage, and the latest releases for HDF5 is 1.10.7, and we have another major release of 1.12.1. And Sherman will talk about a little bit of the difference between the advantage of using 1.12 over 1.10. We also provide the source code. It's open source and it's on GitHub. It's written in C, but it includes optional wrappers for C++, Fortran, Java, and the high-level APIs. High-level APIs are APIs that essentially combine low-level HDF5 library calls to do a certain function. Like if you want to create a data set, it does all those intermediate calls in order to do that. It also contains command line utilities such as h5 dump if you want to view the contents of an HDF5 file, h5 repack if you want to reorder or rearrange the data file itself. If you want to compare two HDF5 files, you can use h5 diff, and we have lots of compile scripts to use those. We also provide pre-built binaries, and we try to include the C, C++, Fortran, Java, and high-level libraries in those builds. And we also include the szip and zlib external libraries in those builds. If you're using, there's also third-party software built on top of HDF5, like H5Py if you're using Python. If you're using C++, there's another contemporary C++ port using HDF5 that supports MPIO that you might look into. Some external resources that you might find useful. So we have the reference manual on our webpage, have the links there. We also have, we try to do weekly group webinars, and our past topics that we've covered in those webinars were introductions to HDF5, using HDF5 advanced features. These especially focuses on maybe some cloud-based usage or HPC type advanced features. And then we've also talked about vol connectors and using vol connectors in HDF5. You can also email the HDF group directly by contacting the help desk, which is the address there. We also have a weekly mini seminar / question and answer session on Tuesdays at 1 that you can ask any questions that you might have for HDF5. And then finally, we have the HDF5 community, which is via the forum. So you can post a forum message and it should get answered either by the community or by the HDF group itself. So let's start looking at a HDF5 fundamental problem, just a simple problem of writing multiple 2D variables over time. So say you have an example of you have P processes arranged in a row column process grid, and then you're looping over time steps where number time step is S. And then you're writing the number of arrays, which of number A, and you're either creating a double array of size, depending on whether you're doing strong or weak scaling, X, Y. And during that time step, then you're just writing or reading the array to or from an HDF5 file. So this is a very simple problem, but it's missing some fundamental information. So for example, how are the array variables represented in HDF5? Are you going to represent those as 2D arrays as written, or do you want to combine them into larger 3D or 4D data sets? Do you know the extents of the data sets ahead of time, or you're going to have to keep extending the size of those data sets as the simulation progresses? You also have to determine how the dimensions are ordered within the arrays themselves, and if you want to organize those data sets into groups. You also have to think about how the data is written. Is that a good way to read the data in that same order for performance-wise? And additionally, you have the storage layout itself. How many physical files do you want? Do you want to do a HDF5 file maybe per process? You want to do you write it to all the processors, write to a single HDF5 file? You also have what type of data set you have that split into. Do you want a contiguous data set or chunk data sets? And are you going to want to be able to compress that data sets on the storage device? So those are all the questions you have to ask before you start actually writing the data. And then you also have to think, as you mentioned before in the previous talks, what file system is underneath and how best to get the best performance of that file system. And then finally, the big impact, one of the big impacts is whether you're going to do collective or independent use of MPIO. So one kind of performance hurdle that we see in HDF5 is it's got a very complex looking interface. but the complexity does not necessarily mean difficult to use. I think there's over 400 APIs in HDF5, but you can really get by just starting off with using less than probably 20 APIs to open a file, create data sets, and then close a file. But some users may require such more complexity in their code to achieve their goals. So, for example, if one of your goals is to be a self-describing kind of shared friendly data layout, where you know you're going to share the data and it has to be really evident what is in the file and what those represent, then you're probably going to have to tune the performance and efficiency with the constraint of using some kind of standardized file format, such as netcdf or CGNS, which is a CFD standard file format. On the other hand, if your goal is just to write the fastest I/O possible with no constraints, if you're never going to share it, for example, if you're doing checkpointing, then you might want to minimize the number of metadata, which means you might want to minimize the number of groups that you have and just write the largest write blocks possible per output dump. So it really depends on the goals of how complex the workflow is of your HDF5 implementation is going to be, and the underlying hardware that might make the HDF5 implementation a little complex. Another performance availability, as I mentioned, is the hardware. How are certain system configurations, activity of other users going to affect your programs? And then the most important part to take away from this talk is the HDF5 property list. These are the H5P APIs in the HDF5 library. And there's nearly 180 APIs. It basically controls the storage properties of the HDF5 object. So it controls the in-flight behavior. So as the program is running, it controls how HDF5 is writing the I/O to disk. And with over 100 different H5P set functions, there's a lot of combinations. So how do you test those? And then finally, the most important part is that if you look at a lot of the APIs and a lot of examples, we use for the property list just H5P default. But sometimes you have to step back and look at those and say, well, what does H5P default mean? And I can tell you that it does not mean most optimized for the system. It means optimized for getting the code running. It does not mean that this is going to be the best default for this particular system. So to do that, you really have to think about how you should just not use H5P default blindly, but just you might have to use other property lists. So you can kind of think of the H5P as a performance go fast code or APIs, or well, it also can make it go slow. So you have to be careful about using it. But you really do start tuning your application when you start to get rid of the H5P default and set property lists. So let's go back to the earlier example of the application model. So there's good or bad news, depending on your view, as that you can have, as I mentioned, you can do several different ways of representing the data, either in 2D, 3D, or 4D data sets. And there are many ways to set their properties. You could do chunking, how you're going to do data alignment, the effect of the metadata block size, whether you're going to do collective or independent. And ideally, in an ideal world, of course, none of this would really matter, and it would all pretty much be the same what you choose. But in the real world, that's not the case. So what we did was wrote a program that kind of explores the HDF5 parameter space and kind of sees how those interact with each other. So what this program does is basically you have a configuration file that sets what properties you want to test. It then creates that HDF5 file. It creates groups and data sets depending on what you want to do. It writes that data, and then it closes the file and then reads the data back in and reports the timing stats from doing that. So let's look at the HDF5 parameter space that we chose. We start with the data set rank in slowest dimension, and I'll discuss that in the next couple of slides of what that means. Then you have an option of doing storage layout. You can do contiguous or chunked, and you can initialize your fill values. So what that means is you can, when you create a data set, if it has no data, it has to somehow determine what the put then that data set? So do you have a default fill value or do you just leave it blank? Then you have other options that control the metadata, such as the alignment and the metadata size. You can choose which library version you want to choose. So you can choose the earliest version of the format or the latest version. And then finally, you have an MPI operations. So if you look along a array, so each of these arrays is a combination of that you can choose from that this program will go through for the parameter space. So go back to the first data set in slowest dimension. You can either have for the IO pattern, you could do a step-based IO pattern where you have your time steps here, step 1 and 2. And then for each time step, you write, in this case, 5 variables of a 3 by 4 dimensional array. Then another option would be to combine those 5 variables into a 3D array. And then finally, the big array, you just combine all the time steps, all the variables into one big array and then write that. So those are your 3 options that we're looking for that the program will go through. The other option is an array-based IO pattern. So here you have your groups and you have your variables 1 through 5, and then you put each time step in instead of for your dimensions. Then you can do very similar what you did before and can combine those time steps into each variable for a data set, or you can then write one single array as before. So now if we look at this, the results of this program, so I ran it on Summit and I'm doing weak scaling where I scale from 42 to roughly 2600 ranks. And then I reorder the parameter spaces from the most scalable here on the left, and then the least scalable going towards the right. And then for each of those corresponding points, I determined what combination of that parameter space gave me the best performance. So you can see for this example on Summit, that if you used a 4-rank array layout with chunk data sets, you don't fill the values, use the default alignment and independent IO, that gives you some of the best scalability. Now, if you were to be unfortunate and you chose to arrange your data to use this side, you would see that your scalability is almost 100 times worse than you would for this case. So this program kind of allows you to play around with different parameter spaces and property lists. And we're continuing to add. The ones that you see here are probably the most important that you'll find in your getting good performance in your parallel program, but we're also starting to add more. Of course, the more you add, the bigger the parameter space, so it takes a little longer to run. So we started with the ones that really what we've seen in the past affects the performance. And for this, we're going to go into tuning, looking at the raw data rights with metadata impacts. And for this, we are using Hack, which Rob talked about in his talk. So what is metadata? It's basically, this is not metadata user defined. This is metadata that the HDF5 library needs in order to describe internally where the data resides. So that, for example, is object headers. It contains what the user's attributes might be, local and global heaps, and B-tree nodes. And these are typically small, metadata is typically small in HDF5 file, kilobytes compared to the raw data. And as a result, when you're writing a lot of metadata, you might have a lot of small writes and small reads, which as we've mentioned, parallel file systems are not very good at doing a whole lot of small writes and small reads. It really likes to do larger writes and larger reads. So for the Hack performance, if we look at our initial implementation, so for Hack, they have a MPI IO only implementation. And so you can see the write bandwidth as a function of number of processes. And this is the blue line is the HDF5 implementation. So you can see that there's quite a performance differentiation between the MPI version that they are using and the HDF5 version. So we looked more into the difference. And one is that when you're using the MPI implementation, they interleave. So when you have, say, for rank 0, Hack essentially has 9 data sets that it writes out. And when you write those, 9 arrays, it will interleave. So rank 0 will write its it's variable 1 right after, or variable 2 right after variable 1, and so forth, all the way up to variable 9 at a certain file offset. Then rank 1 will also write a contiguous set of their variables at the next offset. Now, if you look at the way that HDF5 was doing it, it was having rank 0 starts its variable 1 at a certain 0 offset, and then it will skip in another at the file location at an offset, and then write its next variable 2, and so forth, all the way up to variable 9. You can see that this continues up as you continue the ranks. And now you can also do a similar thing as you see in the MPI interleaved with an HDF5 compound data type, where compound data type is essentially you can write a single derived type with all 9 variables in it. You just write that one derived type. So you can kind of mimic what's happening in the MPI interleaved. So how to match what the pure MPI performance was doing? Well, first you have to find the best stripe size for the Lester or the stripe count using a pure MPI implementation. And what we saw for that was on Lester, the MPI contiguous or the MPI ATF5 individual pattern was better. But then when you went on to GPFS, the MPI interleaved pattern was better. So what we decided was to be able to tune the HDF5 library to match the MPI only performance. To do that, so let's just first discuss on Lester. We set a metadata block size of 8 megabytes, and then we monitor the bandwidth, and you can see that the MPI contiguous and the HDF5 individual can basically, we can give you a similar performance as the MPI only performance. Now, if we go to GPS, you can see that this changes. Now the MPI contiguous and the HDF5 individual gives you the worst performance, whereas if you do an HDF5 compound, so you're doing those bigger writes, it's much better performance than previous. So in conclusion, you have to really know what the underlying file system that you're targeting that could affect your access pattern. You can also, if you have, in order to do some of the, to actually match what the MPI was doing for the hack, we had to introduce a new HDF5 multi functionality that basically can mimic where it controls where the layout in the file each variable is written. We didn't see that much changing to collective IO didn't really help because the request sizes are already pretty big. For MPI interleaved, it was better on GPFS, and then for MPI contiguous, as I mentioned before, on Lester, it was better. Now let's go on to tuning the metadata itself. So, as Rob mentioned, HDF5 is a little disadvantaged compared to PNet CDF because as PNet CDF puts their metadata and globs it into groups at the beginning of the file, so they can control where the offset for some of the raw writes happen, and they can align it to get better performance. Whereas HDF5 has a lot of this metadata spread throughout the file. So if you change the metadata, you might affect the raw data performance. This is a use case. This is again highlighting why you shouldn't probably just use H5P default blindly. So what we saw was that many users report that the H5 close was very slow and it wasn't scaling. And what we found out was that the metadata cache was doing very small accesses from the disk itself. And when it was doing each of those metadata cache accesses for all the processors, that it was slowing down the parallel, it was not doing well in the parallel file system with those small accesses. So what the solution is to gather up all those entries of the metadata cache, create a derived data type, and then issue a single collective MPI write call. So to do that, use the H5P set, collective metadata and collective metadata writes. So what this will do will essentially collect and make a derived type of all those metadata and then write them in one bigger write instead of those smaller writes. And an example of using the H5P set routines to make it go faster, this is for the CGNS library. that's built on HDF5. And you can see that this was on older system for Lustre GPFS, that the original, as it scaled to the number of ranks, was pretty bad. But if you were to turn on collective, the metadata writes, it went basically to 0 for seconds for both the GPFS and Lustre. So that just gives you an example of how you can tune use the H5P APIs to help tune your performance of your application. And with that, I guess I'll take any questions that somebody might have.
Thanks, Scott. We have a couple from Slack. Julio wants to know, is there a way to start with an appropriate stripe size? Like, what's the appropriate guess to start with when you're getting started?
Usually, most facilities have a recommended stripe size of depending on how large the data that you're writing. If you're writing or number of data sets or smaller files, the number of files you're writing. So it depends on for one, the large, if you're writing to a single file and how big those writes are, and how big the data itself it is, then that'll be a different stripe size. So I think if you should probably look at your facilities, because they usually have recommendations. I know NERSC does for what stripe size to use depending on how big the file system or the files you're writing are.
Okay, and then second question, is there a GUI tool for taking a peek at the metadata and knowing variables stored and dimension extents for an HDF5 file? Kind of like a mini GUI version of HDF5 dump. Is there anything like that?
We have HDF view. It's a separate download. It's not downloaded with the source, but it's available on our webpage. You can download it, and then it's more of a GUI. You can kind of click through, and it will show you the file layout as folders and data sets, and then you can actually look at images within the GUI itself. Mm-hmm. That's H5 view.
Someone provided a link there for you, so that's
okay.
Good.